Um, okay, so my name is Rafael Caricio. Today we are going to be talking a little bit about Rust. The title of the presentation is Rust 101. Basically, we are going to uh, see overview of the language. I'm unfortunately not going to tell you that at the end of this presentation we will be like a Rust developer. Um, yeah, you need a bit more time than that or a bit more deeper understanding, but I hope that I can lift some knowledge that you already have from other programming languages that to like get up to speed your learning of Rust, right? So I'm Rafael. I work with software development for about 15 years. Mostly I work with Python, but I always wanted to work in like low level, do some things like more low level in the C and stuff. I always felt a bit threatened. I'm doing something wrong. I'm leaking memory. So Rust was like something that a great addition to my uh, tool sets that I can work on things that I cannot do in Python. Would be very difficult. So I hope you can also see the light. Um, so what's Rust? So they say if you go to the Rust website, you see a language empowering everyone to build reliable and efficient software. So basically, what it means is that Rust wants to enable you to not be afraid to write the kinds of software that are like difficult or difficult to get right? So like highly concurrent software or like low level software or just have a very efficient software that just use the bits that are extremely necessary from your hardware. Rust was started being developed by Mozilla in the research team there, used in the server web browser, like experimental browser, and some parts of this browser went to Firefox. So if you use Firefox, you're probably using Rust if you're using the latest version of Firefox. But nowadays, Rust is mostly developed by the community, so it's an open source project. Is completely in the open GitHub. People can get involved, and many companies like Microsoft, Facebook, Apple are investing in Rust heavily. Like you can see many blog posts from Microsoft, like saying how they are using Rust or how they want to like use more of Rust to solve some problems that they have with memory leaks and race conditions, some things like that that Rust can solve or can help you solve those problems. Of course, Rust is not a perfect language, so there are some flaws. There are some things that you have to understand. It's more like some things are a bit more complicated, but yeah, our language have the ups and downs, and I think that, like personally, I really like Rust. It really empowers me to do uh, great things. Um, so why Rust? Like you might ask. So Rust is a different programming language, but it gives you like performance or like speed of your code executing as fast or in pair or even better than C, C++. You may ask like how can like my Rust code be faster than my like a code in C? C is so low level and how can it be? So what I can tell you is that in some specific cases, the Rust compiler knows more about your intent, more about what you want to do, or what your program, or what you are trying to do with your program, and more information than the C or C++ compiler can get from the C code language. So the Rust compiler can do some optimizations that the C++ compiler can simply not do. So that's this specific cases where we get the Rust code to execute faster than C++. There are some websites that you can see some performance benchmarks on that, and yeah, you can see not always Rust is faster, but it's comparable to C, C++. There is no garbage collector like C, C++. Uh, So Rust, everything, you don't need to manage the memory by hand, but the compiler somehow once can calculate and can infer where your variables can be delocated, can be freed from memory. And this all happens at compile time. And we'll see how this works like in more details during this presentation. In Rust, there is also no represent, or there's no null value. So you not have like any null pointer exception, or method cannot be called null, or like things like that that you can get in Java or in Python. Simply the compiler will, I mean, there's no pointer, and all your code have to work like that without this null representation. You can see like null in Rust, like there is a thing like if you look at some Rust code, you see like none, but that's not a null value. That's just a enum variant. That's called none, and then it may seem like, oh, there is none in Rust, but there's none. And then another thing that's really good about Rust that I really enjoy, I really like as well, is the great support for documentation. Not only for you to write documentation for your code, but also for like things that are already that you want to learn about the language. There's a lot of documentation out there. There is like a free book that I will link in the end of the presentation. There is great tooling between when we install the Rust compiler with the tools for development. There is already like tool for generate documentation for executing like doc tests, like you can do with Python, things like that. Another very interesting thing in Rust are the compiler messages. So the compiler messages are really useful. They try to be very clear, and they try to explain, and they try also to suggest like modifications in your code. Like, hey, you're trying to do this, or you meant this name for the variable. If you mistype something with a typo, the compiler usually tells you, okay, there is a variable here in the same scope with this name. You meant that. So it's really useful when you're like coding and you may mistype something. The compiler will be like like a copilot while you are coding Rust. So it will be always giving you insights on your code or things that you can modify. Another very interesting things with Rust is also the power packaging manager. So in languages like C, C++, um, you really don't have like a standard packaging management or like building system. So in Rust, there is like a build system called Cargo, and Cargo is basically doing everything. There's like a standard way to organize your code and everything. Uh, Not like Python, like you don't know, like some projects have like source folders, some projects don't have, and so on. But in Rust, everything like that is more like the projects are more like standard. So if you jump from one Rust project to another Rust project developed by a completely different company, you'll be able to follow or see what's happening and build, because it's just going to use Cargo, which is the default packaging manager. And also there are multiple packages, and you can just browse them online as well, which is really cool. Another very interesting thing about Rust is the portability. So you can run Rust code like in basically in the browser, in embedded devices, in the kernel, in the user space, like normal applications, which is really interesting. And it's basically like the same code. You just can compile for different architectures, and more architectures are being added every like sometimes some people like, oh, I want to use Rust in risk v embedded devices, and then they just add some new support. In the presentation here, we are going to be talking about safe Rust. There is something called unsafe Rust. Unsafe Rust is a tool that you can use in the language to do some things that you are not allowed or not supposed to do in normal Rust applications. Most of the applications that you are going to ever write is not going to need any unsafe code. The Rust standard library already provides you some tools that you can use instead of writing unsafe code. But I just want to throw this out there because some people are like, oh, but you say that you cannot have some memory errors in Rust, but then there's this error here. Most of these errors are in this layer of unsafety that is basically made to support communication from Rust to other programming languages or other environments. But yeah, let's focus on safe Rust here. How Rust looks like. So you want to take a look. So I just put here this short example of hello world, just a bit more complicated because there is one variable here, but I just want to show here that in this simple example, we can already see some things from the Rust programming language. First, that in the main, you don't need to explicitly say, or in a function that don't return anything, you don't need to explicitly say like what's the return type. So it's really clean there. You just ignore the return type. And also, another interesting thing here is that this name variable, even though Rust is a static uh, typed programming language, there is no type declaration here in this code. What that means is that the Rust compiler, for some obvious uh, types or obvious usage of type declarations, you don't need to actually write that for your code. The Rust compiler will understand, okay, this here is a string slice. You are assigning directly to this variable, so I know that this is a string. Another thing here, we can see there is a print with this exclamation mark. That means that this is not a function. This strange exclamation mark is to say that this is a macro. We are not going to dive into macro system in this presentation, but that's how you print things in Rust. This macro is available in the language. And macro means the same like, or similar things that means in C++. Basically, it means that it can generate this macro expands or transforms at compile time into Rust code. So it will not be compiled directly. There is no function or there is no instruction in Rust language println at the binary level. This goes away during compilation time, becomes some other code here. So that's just a few things I want to highlight in this slide and in this simple example that you can already observe and that you might find it strange. So I would like to talk a little bit about stack versus heap memory. Why I want to talk about this, this might seem strange, but when I was learning Rust, I realized that it's really important for whoever is learning Rust, whoever is using Rust, to really understand the difference between stack and heap. So to be able to decide how to organize your code, or to be able to understand why the Rust language is the way it is, or be able to write efficient code in Rust. So here we have like this simplified picture of a process laid out in memory, how it is. So basically you have going from bottom to bottom up, like we have the text. So basically the binary code that will be executed plus any static text that is in your code. In the previous example, like that string, CBSI would be in this text area. We have initialized data, uninitialized data, so like global memory variables, things like that. And then as your code execute, you have this use of stack. So if you don't do any memory allocation in C, C++, or in Rust, you have just like a stack variables, right? Basically, when you call functions, this stack allocation just create a new scope, and then they're just like piled up and then unpiled. And then if you want to use some dynamic memory, right? If you are reading from a file or if you are using some data that you don't know the size, then you need some kind of dynamic memory, and then is when you use the heap. So you use malloc, you use free when you don't need that memory anymore. And that's where things start to be a bit tricky in C, C++. And that's where language like Python, like Java, Ruby, they thrive with the garbage collector, because then you don't need to worry about uh, allocating memory, deallocate memory, and stuff like this. But then you have the penalty of having this garbage collector running parallel with your code, like demanding resources as well from the machine, right? So your code is not the only thing that's running at that point. Um, and in Rust, interesting enough, you don't need to do explicitly memory allocation or memory deallocation, right? So you avoid any kind of errors like double free, memory leaks, and this is very interesting. Um, and then this in Rust, you don't need to worry about this because the compiler will manage that for you. So basically, in Rust, you will never call malloc or free. There are some other mechanisms that the Rust language use to know when this memory should be deallocated for you. You of course can force it. You can say, oh, hey, I want this memory to be deallocated. There are some mechanisms for that, but in general, the compiler will calculate that for you at compile time, and then your code at runtime, you not have to worry about that. The allocation be already there. To illustrate this, we are going to take a similar example that we saw before, just changing here the types to be more simplified. But we have this variable num, which is number 10 that's stored there, and then we print this value. Basically, this Rust code don't have any dynamic memory allocation. All the types are known at compile time. So we have this number 10, which is the usize type. This is size or a type that exists also in C, C++. I think in Go maybe there is something like that. Basically, this type change depending of the architecture is a pointer size, right? So um, anything if you need to allocate a pointer, this is the size of the pointer. So if you are a machine, yeah, uh, x86 32 bits machine is the 32 bits the U size, and if it's a 64 bits is a 64 bits integer on the U size. But yeah, everything here is in stack, and then the only other thing I want to highlight here is that when we work with some other languages like Python, even though we have this concept of stack and heap, is more conceptual, because in the Python world, like all those variables that you are locating, all these Python objects, they are all actually in the heap. Who is actually using the stack, the computer level, the low level stack, is the VM, right? Is the Python virtual machine. But for us, like for us that are writing Python code, everything is happening in the heap, and the garbage collector works on that, right? Um, And then here we have a different example in Rust. And this is how you throw a value in the heap in Rust. So you don't allocate memory, you don't call malloc. You have like this strange type that I introduced here for you called box. And this box type is basically uh, telling the compiler, hey, I want to throw this number 10, this bytes into the heap, and I want this to be allocated there. So you might think, okay, looking at this, now I have like this box, whatever class or structure that I'm allocating here, plus the number 10. So this is just going to use more memory, is going to make my code like larger and less efficient. Um, Actually, this is what is called like a container type. And in Rust, there are some there's this concept of zero cost abstractions. So in cases like this, there's no actually box structure at your binary level. This code is basically translated and compiled to the most efficient possible way. And this boxes just disappears from the code. And this happens many other data structures also in Rust. These structures, they are good for you to organize your code, but then at the compile time, they just disappear. And in this case, basically, yeah, we are just telling the compiler, hey, I want this number 10 to be value allocated in the heap. And then the compiler will calculate here, hey, this num type, num variable is used up until line 3. And then line 3, the num variable goes out of scope. When the variable goes out of scope, and the compiler can calculate that, it will just put there instruction that will deallocate the memory. And that instruction is the drop instruction. So you can see here I put explicit because, as I said, you can control as well when you want things to be deallocated. And in this case, to do that, you just call a drop. And a drop is a mechanism that you can force a variable to be invalidated, to be removed from scope. After that, this variable is invalid. But as I said, you don't need to put that. The Rust compiler is going to calculate and is going to put that there for you. And this memory is going to be free. In some other language like Java, there are some optimizations that will not deallocate the memory immediately. The Java virtual machine might decide or usually decide to not deallocate memory, so it just grows, and then it's just there to be reused one day if necessary. In Rust, the memory is really deallocated at that moment, so you can keep your memory usage exactly where you actually need. Another examples of uh, values that go to the stack, go to the heap, um, are like these complex data structures, right? So even though most of the variables that you use, they are by default allocated in the stack, when you use like a vector, when you use a linked list, when you use a hash map, a hash set, those structures, they don't have a size known at compile time. So those structures need to be allocated on the heap, have to make use of the heap memory. And again, you don't need to worry about deallocating these structures. The compiler will figure it out for you how to do that. And if you have specific like types, like you're just an integer that you want to throw, you can use the container type called box, and then you to throw the memory into the heap. Um, so as I said, like memory, the heap memory is to deal with this dynamic data that cannot be known at compile time. Um, yeah. Another thing that you hear a lot when learning and when using Rust is something called lifetime. Here I just showed here that the new box value is goes out of scope in the line 3, right? So it doesn't exist after that because that's where the curly braces that limit the scope. So sometimes things like that happen, like they scope the lifetime of that uh, value, like that box number 10, is matched to the scope of the variable match the lifetime of the data, right? So in this case, it's a very simple case that the variable just go out of scope and is deallocated. In cases that the variable or the value is not deallocated and doesn't match the scope of the variable, is when there is a thing called a move or a ownership change. Because in Rust, there is this concept of ownership, and basically what it means is that the value num owns the value of the box. So this memory the box allocates, or this value that's the box belongs to the num variable, and when the num variable goes out of scope, it also gets allocated. But you can keep the memory in the heap existing for longer if you can move this value or move the ownership for another variable that will live longer than this scope. So let's talk a little bit about ownership. Ownership is a key concept in Rust for the case of why Rust or how Rust don't have a garbage collector. So the ownership model of Rust allows the compiler to be your garbage collector at compile time. So the the compiler makes heavy use of the ownership semantics in the Rust programming language to calculate these drops where the allocation of memory is going to happen. Uh, so you can have these ownership changes in the code, in your Rust code, when you assign variables to different other variables. And yeah, we'll dive into a little bit more on that. First, let's take a look at three simple rules of the ownership model. This is the whole ownership concept of Rust. It's basically these three rules that say each value in Rust has a variable that's called its owner. So in that case, that example we saw, the num variable is the owner of the box, is the owner of that value. And there can only be one owner at a time. Time here is the scope. So in every scope, where a variable, where a value lives, can only be one variable that owns that value. When the owner goes out of scope, the value will be dropped. Like I said, when the owner of that variable, if that variable didn't change the ownership, didn't move to another variable, that value is basically deallocated, is dropped. In Rust, we don't call freed, or we don't call deallocated, we call dropped. That's why the method, as you saw in the previous slide, is called drop. This is a bit complex, right? So let's try to see some examples so we can try to understand better. I think a good example is when we start discussing the string type. In Rust, the string type is a bit different than other programming languages. There is more than one string type, or it seems like there is more than one type, more than one string type. Um, but because Rust sees string not doesn't incorporate strings between be, built in the language. String in Rust is a structure, and there are different kinds of structures, different ways you can represent a string. In this case here, we have this ampersand string, and then this is the type of this name. So when we assign just a quoted string, like a string in other programming languages, to a value in Rust, the actual type is going to be this ampersand str. What that means is that this value is actually a reference. This ampersand, whenever you see an ampersand, is a reference, like a pointer, right? So this is a reference to a place where there is this string, immutable string, Rafael. At compile time, these strings, these literal strings that are spread in your code, they move to this. If we remember the memory layout, right, of the process, there is this part where there is the text part. These strings, these literal strings in the code, they all move, they all put in this part of the memory. And that's why when you have a variable that you assign this value of this string, it's just a reference to this immutable string memory region. So that's why this string is not mutable. And then you may ask me like, okay, so if in Rust all the strings are immutable, how do you do string manipulation, right? So in Rust, we have a different structure that you can use, that you use to manipulate strings. Uh, Basically, the structure that you use to manipulate string is called string. So there is a struct that's called string, and that struct, when you use that struct, this string is not anymore a pointer to a string in this text area, but actually a value in the heap, right? So this string is a is a section of memory in the heap, and then you can do things like manipulate this string, like change the string, concatenate new values. And here there are a couple of things that we can take a look. First is that we are using this new keyword called mut, and this is to say that this value that this variable points to, or this variable is mutable. So we want to change this variable. By default in Rust, all variables are immutable, right? So if you want to change, or if you want to make this variable be able to be changed, you have to say mut, and then the compiler will also know and will also be able to do optimizations for that intent that you want to use. So again, the string here is allocated in the heap. The string that you see there, like the Rafael string, is a reference to this section of the memory. So when this part of the code executes in line 3, this memory is allocated in the heap, and this string, this immutable value that is there in this text part of the memory, is copied to this heap memory, and then you have the string structure here. And the other thing is that the string value there in Rust, the string struct, is basically a wrapper in a vector. So there is a capacity, there is a size, and when you do things like push string, it will verify if the string has this capacity to incorporate this extra amount of bytes, and then it might allocate again and move to a different part of the memory. And that's why you have to have this mut, because this is going to change the memory, is going to change the values inside this string. And here we basically just concatenate with space Caricio, and then we print it. And here we have this internal scope, which basically just to like is unnecessary. It's just I added there just to say that in this end of this curly brace, the string will be dropped, will be deallocated from the heap memory. And then at the line 10, the variable name is out of scope, and the value of the string, the memory that was allocated there, is free completely. Yeah, and this structure of the string, this struct, allows you to do things and allows for some flexibility on a string. Because string, if you code in Python, you know string is not, or in any programming language, you know that string is not like an easy type. Like you have encoding problems, you have characters that in different foreign languages they may be mut bytes size. So in Rust you have this abstraction that you have some helpers to work with this kind of things. Yeah, and the variable name here, that's what I'm saying, just owns the string, right? So when it goes out of the scope, the memory deallocated. Another example here, this is a very interesting example because you might look at this and say, okay, I don't see any problems here. This code just have a variable name. I create a variable n2 and then I print the variable name. Actually, in Rust, this is not going to compile. There is an error here, and this error happens because in the line 3, we have this assignment from the variable name to a variable any2, which basically moves, and that's this n2 variable is the new owner of the value string. So what happens is that the string is not deallocated, but the variable name is completely invalid by line 6. So the compiler is going to give you an error here and say, hey, this usage of name here is not valid. And the error you get is something like this. So this is actual error from the Rust compiler that you get if you try to compile this code. So if you look here at this error message, you see some strange names like borrow, like what borrow means. We'll get there, but for now, let's just focus here that the compiler, what the compiler is telling us. So the compiler is telling us that the value moved in this specific line, and here in the line 6, you try to use this value after the move, and we try to borrow it. And what that means? That means that when you print something, this macro, this print string, println, is not going to take ownership. It's not going to take ownership of the name. It will simply borrow it or take a reference of the variable that you use in the arguments there. So there are ways that you can use or you can assign the value of name to a different variable in a way that will not move the value. So to do that, uh, we can use this concept of borrowing, which is basically taking a reference. It's very similar to C, right? You use the n% as well. But in Rust, you have two types of borrowing. You have a mutable borrow, which you use the mut keyword, and you have a immutable borrow, like the first example here, that you just use the ampersand. The borrow is basically like a pointer, and the borrow, as I said, doesn't change the ownership of the variable. So that's the usefulness of the borrow. It's just when you want to use this variable, but in another variable, another context, in another scope, but you don't want to take ownership because you don't want that when it goes out, your code goes out of that scope, it deallocate this memory. So let's see how we can fix that example again. So as I said, the macro println will not take ownership. It will try to take a reference, try to borrow that value. And to fix this, we can just use the ampersand as we saw in the presentation here. So we say here now that we are just assigned to n2 a reference or a borrowed, an immutable borrow of the variable name. And then when you use in line 6 the variable name, you can in the println put explicitly that you want to borrow, but it's not necessary. The macro is going to add for you. But anyway, the code is going to compile now, and it's going to execute the way you would expect in different programming languages as well. It's just that Rust, you have to be more explicit about this kind of thing. Here there is a more elaborate example about this use of borrowed. So just to illustrate in different context, more elaborate context, where this borrowing rule or borrowing concept would be useful for you. So here we have the S1 variable in line 2, which is string hello. And then we call this calculate length, and then we pass a reference to S1. We get the length of the string, and then we print it, right? In the case of line 6, we print the S1. So we need the S1 variable to be still valid, and that's why we use the reference there. And if we look at the implementation of calculate length, you see that we just call the length method. And when this S variable goes out of scope, since it's just an immutable reference, the string is not deallocated, right? So the string is still valid when the execution of the code goes back to line 4. Another interesting thing here, and that's where things get interesting as well, is that just looking at either the call of the calculate length in line 4, or looking at the declaration of the function calculate length on line 9, you know already, just looking at this, that this function doesn't change the value of S1. You are like explicitly saying here, you're explicitly visible that the calculate length is a safe function to call, or call even multiple times, because the string is not going to be modified. This is very interesting because in language like Python, Java, or Go or C, you don't know like okay, I think in Go you just pass by reference. I don't remember now. But anyway, it's very difficult to know if things are going to change, or if this value of this variable is going to be mutable there inside this new method that we're calling. You basically give all the credentials to this method to do anything it wants. And this, for small code bases like this, is very like useless or not necessary. But when you have a very huge application, very big application with thousands of lines of code, and you want to do some refactor, these things become very important. On the side here, we can see that how these variables are laid out in memory. So the S is just a pointer, right? So just a reference. And the S1, as I said, is a struct that contains the capacity and the length. Is a vector, right? And then the index, these values there on the far right is what is in the heap memory, right? So this is the dynamic part of the string. There are some rules about borrowing as well, so the compiler can do its work. Uh, the first rule of borrowing is that can only be in the same time, or which means in the scope, can only be one mutable borrow. Uh, and the other rule is that there might be multiple immutable borrows at the same time. And then you can start to think like, okay, why this rule exists? This rule exists for something like you call, or you see here R1 variable is pointed to the string, and it's pointed to that memory address. And then there is another part of the code that in line R3, you get a mutable reference to this variable, and then you change the size, you append some bytes to this string. And then what happens that this variable change the memory address. When you change the memory address, the R1 becomes invalid because now it's pointing to this invalid memory address. So that's why the Rust compiler will check, you verify these borrowing rules and say, oh, okay, you cannot have um, mutable reference while there is in the same scope immutable reference. Right? So in this case, there will be a problem and the compiler is not going to let this code compile. And this is the kind of error you get. So in line 6, so the compiler always, like as I said, the error messages are really expressive and very useful. So you can see here, like it's so, okay, here in line 4, you have this immutable borrow here, and then in line 6, you try to do a mutable borrow. And here in line 8, you have a use of this immutable borrow. So this R1 variable is still valid, or has to be still valid on line 8. And that's why, like, if you remove the R1 from line 8 and R2, obviously, then you would be able to use R3, because then the compiler would be smart enough to see that the R1 and R2 variable can be deallocated in line 5, or can be invalidated at that part of the code automatically for you. And then the R3 variable, which is the mutable borrow, is the only leave alive reference to S, and only one use after that. So the code would compile. Now you might be like, oh my God, this ownership, this borrow, and this stuff is so complicated. I need to really put this in my mind. Is very difficult. But as anything, these things get really uh, easy, like with time, with practice. Naturally you start like looking and verifying this even before the compiler tells you. In the beginning you get a lot of what people call fights with the compiler, but I would say it's more like coaching. The compiler is telling you, hey, here you forgot, you uh, took a mutable borrow while you already had a immutable borrow, and then you be able to try to rethink your code, how to organize your code in different ways. But another thing and a good news here is that you right now just had a glance of the most complicated part of learning Rust. So these are the most complicated concepts that you need to understand when you are learning Rust or when you are using Rust. And if you think that you can handle it, or that it's you just need a more reading and stuff, you are ready to learn Rust. Or even if you think that you don't understand, which might be the case because this is just a quick presentation, uh, you can just read like more about that and understand, and then you'll be ready to get more understanding of Rust. Everything that's going from now on about trust is going to be more natural. It's going to be like more familiar for you since you used previously different programming language. So let's take a look in some parts of Rust that's going to feel familiar for you now that we saw these completely crazy different parts of Rust. First, I want to show you like struct. So struct in Rust is basically very similar to a struct in C++. In C, yeah. So you have the struct, you have different types. You can have different types in the same struct, and yeah, you can instantiate the struct. You don't have inheritance in Rust. There's no it's not object oriented language, but there are some ways that you can apply some of the object oriented uh, um, patterns in Rust adapted to use of things like traits. Traits are like interfaces in Rust. Um, but I would say it's more like, it's not like interfaces in like language like Go, because in Go you cannot have like default implementation, I think. Um, but in Java, for example, you can have default implementation for some methods in the interface. And in Rust traits, you can have that as well. So it's similar to the interface in Java, but I would say it's a bit more powerful than that even. Here we take a look a bit of traits, like let's see how it goes. So here in the product is the same struct that we saw before. Um, I just put in one line, so it's easy to see. As I said, the trait can have like some default implementation. And one interesting thing here that for Python developers you'll be familiar is that we have this self again. In Rust, we have this for methods, so that's how we identify that this method demands that this whoever implements this trait, you have to be instantiated to this method to be called. Uh, and then here in the line 9, we see the implementation for the trait priced for the product construct here there. You see that the implementation of the interface is separated from the implementation or from the declaration of the struct. And another thing that is very interesting here is that, like in Python, when you call the get price on the variable p, which is an instance of product, in line 21, we don't need to pass self. Like this is implicit as a thing that the compiler will add for you. And another interesting thing that is different than Python, even though there is a self here, is that by the signature of this method, we also know that this calling this method cannot change the value of this, like the properties of the struct product. We see that there is an immutable borrow on self there. If you want this to be a method that can change the product properties, you have to put like a percent mode self, and then you can. This is why in Rust there is like these signatures that are a bit more complicated, but they mean something. They give the compiler this more clear view on your code, what you want to do, and then you can execute. You can perform better like optimizations. Here we have the enums in Rust, so you can have different enum variants. You can have different enum values for those variants, like you can hold values there. And the enums can contain associated methods, so you can implement traits for enums as well. And the match zone enums, like in line 9, they are exhaustive, so you have to use you have to match to all the arms of the enum, all the variants. But yeah, of course, you can define like a default arm that will execute in case it doesn't match the other ones. We have also generics in Rust. I just put here just to illustrate. I will just quickly try to go through this. So we have the value a, so we declare like this less than and greater than a, just say that there is any type. So you declare this generic type, and then you make use of the generic type in sum. And then we have the variant none. So basically that's one way that you can have that representation of no value in Rust. You can declare yourself enum, or you can use some other enums that the language provides for you for that. Another thing here, by the signature, you see that there is this B, which is different than A, but it's just saying that here in the value, when you say value B in this line 6, you are basically saying that this value you have to be associated with this whatever type in B. And this type B has to implement the trait display because we want to print it, right? So we want to display it, we need to be able to transform this in a displayable information. So that's why we need to declare that we want to have this, we require this trait to be implemented for whatever this value is. And then here we see some calls to this method, and line 14 and line 15 basically use the same implementation. So this sample here is the reference to string, right? So they use with the same method. And here, on line 15, we are just saying that explicitly we want to call the variant or the implementation of print value, the instance of print value that is for this type. And in line 16, we are saying that we want the implementation of print value for the unsigned integer 8 bits in that line. So the compiler basically is going to take the print value template function and then create two implementations of this function. And then there will be in this specific code for reference of string slice and for unsigned integer 8 bits. So just a bit more complicated here. And this is what's called in Rust turbo fish. So when you see this combination of characters, people call turbo fish because it looks like a fish. So that's how people call it. Just a curiosity. So now let's see. We saw a bit of Rust. So what can we do with Rust, right? Like that's the interesting part as well. You can do many things in Rust. The scope is limitless. But just to illustrate a little bit, we can write operating system. There are some operating systems written in Rust. The Linux operating system wants to see ways that they can accept patches in Rust in the Linux operating system. You can write device drivers for Linux and for other operating systems in Rust as well. Rust can run in userland, or you can run like in hard mode. So you can write bootloaders as well in Rust. You can write firmware applications for embedded devices like smartwatches, keyboards, mouse, things like that. You can write web applications in Rust. Like you can write backend systems like web APIs, REST APIs, but you can also write front-end one-page, single-page applications in Rust instead of JavaScript. And you can basically exchange like some crates, some modules, let's say, parts of your code between the backend and the front end. and then you don't need to write any JavaScript, or you just have Rust in the backend and in the front end. And that's very interesting. This is one of the advantages. People say, like, they want to use Node in the backend, right? So they can interchangeably share code from the front end with the backend. So in Rust, you can also have that. It's just that in Rust, the page is going to be a binary WebAssembly that's going to be executed in the front end, in the browser. Rust also have very good integration with multiple programming languages. In this website, you can see some examples, like short examples, how to integrate Rust in different programming languages. So it's very interesting. I recommend you to take a look on this website. Here's just a quick example how you can write a full Python module in Rust that you can import in your Python code and use. So here you see in line 6, we just have this sum as a string method, basically sum two integers and then return a string in Python. And then you have the declaration of this module in line 12 that exports this function to the Python virtual machine. So there are some modules in the pip Python package manager that are implemented in Rust, really. Here, there's another example of what you can do with Rust. You can write some pictures here. You can see some embedded devices that displaying some graphics, and this is implemented in Rust. And then you see here these windows with some graphics as well. This is the same code that's running in those embedded devices, so that can be flashed in those embedded devices, but compiled to WebAssembly. And then you can see in the browser, or you can see in the browser, okay, this interface is really cool. I want to have this run in my embedded device. So you can just compile it to your firmware and then flash in your embedded device. So that's really interesting as well. Bring it a bit to our world here in video processing. There is this AV1 encoder that's implemented in Rust. Like many companies are involved in this effort, like Google, Microsoft, Amazon, Mozilla, and it's really interesting to say that's the fastest AV1 encoder. So that's very interesting as well. Another example is the JStreamer support, like JStream port of like interface of Rust. So basically, there's a Rust crate that you can use, and then basically it's JStreamer. So there is this bindings, that's how we call when you export a Rust C library or a library in your programming language to Rust. You say like I created bindings for this library in Rust. So in this case, there is a bindings for JStreamer, and I actually use these bindings in a recent project I worked in the live squad called Hawkeye, and I'll be presenting about this project tomorrow in the Melbourne live meetup. That's going to be live stream, so you can see it's probably going to be recorded. I can post about that as well. Where can I start? So that's like you were asking me, where can I start learning Rust? I would recommend reading the Rust book. This book is available for free online to read. So you can just go to this website, it's in the Rust programming language website, and you can read online. That's how I learned, that's how I read the book. You can also obviously buy the book like in hard copy. Also, there are many other resources that you can look in the Rust website, podcasts, conference talks on YouTube, blog posts all over internet. So people are really interested and really talking about Rust everywhere. I hope you enjoyed this presentation. I hope you enjoy learning Rust. I'm available and hanging around in the Rustlang general channel in our Slack. I'm happy to talk about Rust. I really like Rust, and if you have any questions or if you want to discuss something, I will be happy to talk to you. Um, yeah, and I think that's the end of the presentation. Um, I don't know if we have time for questions, but yeah, thank you.